The experimental setup by Millikan and his PhD student Harvey Fletcher. You see that if we notice on the right hand side figure, you see the tank with the telescope and atomizer. You may have a question, teacher ครับ ตัวนี้ teacher ครับ what is atomizer? And if you look closer for the component of the atomizer, actually it's like a device that you use in your house, or we call the spraying device. Definitely this device is we use it for the spraying an oil into the oil drops, right? However, when you try to look closer for the tube of the atomizer, you see the tube is quite long. And for the purpose that we use the long tube, because we want to make sure that we have the triboelectric between the wall of the tube and the oil drop, or the friction effect. And as you can learn from the electrostatic, did you still remember when we have two surfaces and two surfaces they rub together, it causes the electrostatic charge, and therefore definitely the oil drop from the atomizer, we have like a frictional effect or triboelectric effect, or roughly speaking, all of the oil drop from the atomizer, they have already ionized, but we have no idea which charge they are. It may be positive or the negative charge. But for my explanation, I use the negative charge for the oil drop. So you see, when the oil drop is going out from atomizer, definitely it must going down because of the gravity, and it's going into the chamber D in the left figure. And in chamber D, if you look closer, we have the plate M and the plate N. And if you try to look on the plate M and the plate N, you see M refer to the top plate, and this top plate is connected to the positive electrode, and N refer to the bottom plate. This bottom plate is connected to the negative electrode, or it means that the space between M and N plates, there is an electric field. And definitely we try to balance the gravitational force on the oil drop with the electrostatic field in the M region, right? But in any way, just take a look closer in the MN region. And if you look on the right hand side, you see the tube with the spherical shape at the middle of the tube. What do you think? What is this device? Definitely, this device, we are referring to the notation X if you try to notice carefully. And this device is referred to the X-ray tube. And you may ask me, teacher, why we have to use the X-ray tube? Definitely, I will try to tell you later. And from this experimental setup, it means that we try to balance the gravitational force and the electrostatic force together in the region between M and N plate, right? However, just keep in your mind that can the charge or can the drop be at rest? No, definitely. We hardly see the oil drop at rest, and therefore if we see the oil drop moving in the air, it means that we have to consider the air resistant as well for our free body diagram on the oil drop. And therefore, for the Millikan oil drop experiment, we have at least 3 steps to getting the data. So let's go to the first step. For the calculation of the elementary charge of electron in Millikan's oil drop experiment, there are at least 3 steps that we have to use for this experimental setup. The first, Millikan and his PhD students, they have to select the drop that they are interested. For example, they have to select the drop with the charge equal minus Q1, and just let the drop that he is interested is falling into the region between the positive and the negative electrode. But first, just keep in your mind that we just turn off our electric field. And therefore, when the drop is falling down between this region, you see, actually it's falling down with the charge Q1, right? And with the falling speed V0. And from this one, if I asked you which kind of force that acting on this oil drop, can you tell me? Definitely, when it's falling down, it must have the gravity that acting on this drop. And definitely for the gravity can be written as mg, and mg should be equal the density of the oil multiplied to the volume of the oil. In this case, the volume of the oil, we assume that our oil is like a perfect, it's like a perfect sphere, and therefore for the perfect sphere, the volume of the oil drop can be written as a form of 4/3 multiply radius to the cube multiply g. And I think it's quite obvious for mg, right? And the next, which force that we have, definitely when our drop is falling into the medium such as air, we have to consider air resistance, right? And usually for the air resistance, or I use the notation FV. FV is like an abbreviation for the viscous force that actually we have to use Stokes law for the calculation. And mostly for Stokes law, if you want to calculate the viscous force can be written as FV equal 6 multiply pi multiply eta. Eta is like a dynamic viscosity, multiply the radius of the drop and multiply V0. That is the magnitude of the viscous force that we are interested. And what else? What do you think? Which force that we have to use for the determination of the motion of the oil drop that we are interested? Definitely. You see, our oil drop is in the air. Not only just the viscous force from the air, but you have to consider buoyant force is like an object in the fluid medium. And therefore, for the viscous force, I use the notation FB. FB can be written as the density of the fluid multiply volume and multiply G. And in this case, FB can be written as the density of the air multiplied to the volume which is substituted by the object. And this volume, definitely it should be the volume of the sphere or the volume of the oil drop multiply G. And from this system, you see, we have all forces for the determination of the motion. And from this video clip that I have already uploaded, you see, most of the drop we assume that is moving with the constant speed. And therefore, when it moves with the constant speed, we can write equation of motion like Fv plus Fb should be equal mg. Now, I think it's quite obvious for you. And therefore, when you just substitute the value of Fv and Fv and mg into this equation, you will get like a 6 multiply 6, sorry, should be 6 pi eta or V0 multiply rho of the fluid. In this case should be rho air multiply volume that is substituted in the fluid equal mg, and this case should be m of the oil drop, and therefore for m of the oil drop it should be the density of the oil drop. I use rho o multiply the volume of the oil And this one also, I think is quite obvious for you. And therefore, if you try to look for each parameter that we are interested, for example, for the dynamic viscosity of the object in the air, I think it's like available information that you can find from the engineering data book. And therefore, from this one, you see, V naught is like a falling speed of the drop that we are interested. And from the video that I have already tell you, we are able to calculate the falling time, and from the falling time, you should be able to calculate this value as well. And therefore, for the density of the air, do you know this value? I think yes, you are able to calculate, or you can look from the engineering data book, and also for the density of the oil. That is the value that you can find from the engineering textbook as well. And definitely, you have only one variable that you have to calculate. In this case, you have to calculate the radius of the drop that you are interested. And from this equation, if you try to rearrange the variable, finally you will get the radius of the drop that you are interested from the first step of the experiment. It should be equal square root of 9 divided by 2 multiply dynamic viscosity multiply V naught, or the falling speed, divided by the difference between rho of the oil minus rho of the air multiply gravitational acceleration. And therefore, that is the first step for the calculation in Millikan oil drop experiment. We use this stage for calculating the radius of the drop that we are interested. So in the next step, we still use this drop, but in any way, we have to switch on our electric field. Let's take a look closer for the second step in the Millikan oil drops experiment. As what I have already mentioned, we still use the same drop that we select from the first step, right? And therefore, from the first step, we have already calculated the radius of the oil drop. So for the second stage or second step, we just turn on our electric field, and therefore when we turn on electric field, definitely our oil drop will experience the force from the electric field, and therefore when our charge that we are interested is the negative charge, as you can see, the force from electric field must be in the opposite direction of the direction of the electric field. And this one, this electric field will pull up this oil drop with the terminal speed equal V1. Okay, may I ask you a question? From this system, when electric field is turned on, if we want to write down the free body diagram in this step, which forces that acting on this oil drop? Can you tell me? Definitely, this one, because in any way the oil drop is in the effect of the gravity. We have to consider the mg, or the gravity on the oil drop. And therefore, when we have to consider that our oil drop is in the air, we have to consider the buoyant force, or Fb, as well. And for the direction of the buoyant force, or Fb, the direction is upward, right? And therefore, you see, our drop now is moving, or it is rising. You see, when it rising in the air, it means that we should have air resistance in the opposite direction to the motion of the drop. And therefore, in this case, we should have the viscous force from the air resistance. And therefore, if we assume that our drop is moving with the terminal speed or with the constant speed, if we just use the first law of Newton, we should be able to write down equation of motion like this. And therefore, for the equation of motion, F from the electric field plus F from the buoyant force, right, should be equal F on the viscous force from the viscous force plus mg. I think you agree with me for this equation of motion. If we assume that our drop that we are interested, they are moving with constant speed and therefore no acceleration. And from this stage, as you can see, you should be able to write down the force from the electric field should be equal Q1 multiply E. And force from buoyant force should be the density of the fluid. In this case, should be the density of the air multiply the volume of the object. It should be 4/3 multiply pi multiply r to the cube, or the volume of the sphere multiply g. Now, this case viscous force, when we apply Stokes theorem, it should be equal 6 multiply pi multiply dynamic viscosity, or eta multiply the radius of the drop that we use the same radius as usual multiply v1, which can be calculated from the rising time that we observe from our experiment. And this one should be m. In this case, should be m from the oil drop, and m from the oil drop should be equal rho of the oil drop multiplied to the volume of the oil drop, which we assume that is the sphere. Okay, when we try to look closer in this equation of motion, you see, from now we know this value already. Now we know the radius of the drop already, and from this step, which parameter that we want to calculate? Definitely we want to calculate the charge of the oil drop from the atomizer. And from this step, if you try to rearrange the term a little bit, you will see that the charge that calculate from the first time, or the charge of the oil drop from the atomizer, can be written as a form of 6 multiply pi multiply eta multiply v1 plus v0. v0 is like a first falling speed, and v1 is like a rising speed in this experiment, multiply square root 9 divided by 2, and multiply eta multiply v0 divided by the difference between rho of the oil minus rho of the air multiply g divided by the electric field that we have already turned on. And you see, from this first step, you should be able to calculate the charge of the oil drop from atomizer. So let's go to the next step about changing the charge of the oil drop. For the third step, for the determination of the elementary charge of electron, so we still keep our electric field turned on. However, we have to irradiate our system by using the X-ray radiation. And therefore, if you just look for the property of the X-ray radiation, you know that the X-ray can ionize the air in the chamber. And therefore, when the air is ionized, it might be possible that the charge that we are interested might change the value of the charge. For this one, it might be possible that the value might change from Q1 into Q2. And therefore, when the value of the charge is changed You see, now definitely we have to change the magnitude of the force, and when the magnitude of the force is changed, you see, now at the beginning, now this charge is moving with the air resistance, but finally, now when they move for a while, now this oil drop will reach now the terminal speed with the speed equal V2. And from this one, as you can see, if you just look at the free body diagram, you see that our free body diagram is quite similar to the free body diagram that you have seen from the second step. You just change the value from Q1 into Q2, and also from the rising speed from V1 into V2 as well. And from this one, if you try to rearrange this value, to calculate for the Q2, I think it's quite straightforward that you just calculate the V2 as a function of 6 multiply pi multiply eta multiply V2 plus V0 and multiply this square root eta V0 divided by the difference of the density, multiply G and divided by the magnitude of the electric field, that we just keep it constant. And from this step, as you can see, I think Millikan and also his PhD student, they try to irradiate this system many times by using the X-ray tube, and you can imagine that there are a lot of data about the change of the charge from Q1 to Q2 and also to Qn if we just irradiate n times. And from this data, they just assume that the Q from Q1 to Q2, they just assume that from Q1 to Q2 to Q3, it should be written as the integer number, for example, equal N1 multiply the elementary charge, or it should be equal just the integer number multiply elementary charge. And they use the mathematical formalism, just plot the graph and try to find, in Thai we call holomor or coronal or something like this, to calculate the elementary charge. And finally, from this experiment, Millikan and his PhD students, they were able to calculate the elementary charge of electron equal 1.6 times 10 to the power minus 19 coulomb. And that is one of the great discovery for the value of the charge of the electron. And from this one, if you still remember from the experiment by J.J. Thomson, as you can see, Thomson, he just know the ratio between the charge of electron and the mass of electron equal 1 times 10 to the power 11 coulomb per kilogram. And from this discovery by Millikan and his PhD student, they were able to calculate the mass of the electron. And for the mass of the electron, definitely the mass of electron roughly equal 9.11 times 10 to the power minus 31 kilogram. And that is all for the calculation on the Millikan oil drop experiment. I hope that you understand this explanation more or less. But in any way, if you don't understand, just take a look for some example.